Good afternoon, everyone. My name's Jessica and I am a project officer here at the CPD unit at Cardiff University. Thank you so much to everyone for joining us this afternoon. Just a few housekeeping bits. We are all still working from home at the moment. So if there are any interruptions from small children, pets, or poor Wi-Fi connections, please bear with us. Today's session is designed to be a taster for Professor Tom Blenkinsop's online course, Structural Geology for Exploration and Mining. Bookings are now open for that course, and we will send you an email with any information following this session. Please feel free, as it said in the video, to put any questions you might have in the Q&A box, and we will get to those at the end of the session. And also just a reminder that the session is being recorded. All of the recordings of our Spring School sessions will be available on our YouTube channel at the end of the Spring Online School programme. It's just left for me to hand over now to Professor Tom Blenkinsop. Thanks very much, Tom.
Good afternoon, everybody, and thank you very much indeed for that introduction, Jessica. So in the next 25 minutes or so, I just want to give you a quick sort of taster of the Structural Geology for Exploration and Mining online course, which has been running here at Cardiff University for over a year now, and has actually attracted participants from all over the world in quite significant numbers. It's designed really for professionals working in the mining and exploration industry. And what it is meant to do is to help establish some principles of how to go about exploring for important resources for those people who have already graduated with some sort of earth science degree. So it's sort of a revision program, and also introducing the more specific aspects of structural geology concerned with exploration and mining. Now, the background to this course is, of course, the pressing need that we have to transition into a green economy and the enormous implications that that has for resources. So we mine metals out of the Earth's crust, and we are going to need a huge increase of some metals in order to transition to the sorts of renewable energy which are going to replace fossil fuels, such as solar cells or wind turbines. Now, to get an idea of what's involved here, we can look at the periodic table and highlight some of the elements we're going to need to make the transition to these non-fossil fuel-based energies, such as fuel cells, batteries, photoelectric cells, or turbines. And while some of these elements are very familiar to us, iron, nickel, copper, the base elements, there are a variety of newer elements, such as these platinum group elements down here, or the rare earth element groups, which are specifically needed for these new applications. But it's worth mentioning that in spite of the need to find these more exotic elements in the periodic table, we're still going to need huge quantities, even more than ever, of the familiar base metals. And that poses a huge challenge to us, because even if we take something like copper, which is a relatively common mineral in the Earth's crust, forecast suggests that we're going to achieve peak copper production within the next 10 to 20 years, after which, based on our existing knowledge of resources, production will decline. And this is a serious problem when we consider, for example, that a fully electric vehicle requires 4 times as much copper as an internal combustion engine powered vehicle. So that has great implications for geologists and structural geologists in particular. Where are we going to find these extra resources that we so urgently need? I'm going to illustrate that with a resource that's perhaps not so vital for the transition to the green economy, but it does illustrate the point very well. You're looking at a map of gold mines in Zimbabwe, colored according to their production. And it teaches us one very obvious and important aspect of looking for resources, which is that they are fundamentally clustered. They don't appear everywhere in this map of Zimbabwe, or of course, over the whole surface of the Earth. They're clustered in concentrations of very high producing areas. And we can understand some of the reasons for why the particular resources are clustered in certain areas if we simply look at a geological map of Zimbabwe. Those mines are indicated by the various symbols here, and they're very clustered along the contact between these two rock types, shown in sort of pale and pink colors over here and in green colors over here. So there's a very fundamental geological control simply in terms of rock types on where we're going to find these new mineral resources. That's been known for centuries. What is less well understood is that in addition to the basic rock types, we also need to focus on structures. This is a different map of the same area in which the structures which control those deposits are indicated by these black lines. And if we compare that with that previous map, it's very clear that actually most of those gold mines are sitting on one or other of these structures. So structural controls on mineralization are absolutely fundamental. And that is what the whole of the course on structural geology for exploration and mining is based. Now we see that at the scale of maps like this. We also see it at the scale of individual deposits. When we look in more detail at where gold is actually contained within the crust, it's contained along a variety of structures, such as the ones that you see in this collage here, including veins. Here is a spectacular occurrence of visible gold in a quartz and carbonate vein at Sunrise Dam in Western Australia, Australia's second largest gold mine. Here's another form in which the gold ore occurs in these fragmental rocks called breccias. And here's a third form at that same deposit in which we see a very penetrative foliation of fabric in this rock, which contains the gold mineralization. Other deposits combine different aspects of those 3 different things. Here, for example, from Geita Gold Mine in Tanzania, we see a zone of deformation in which we can identify veins like the ones immediately above it, but we can also see in the intervening rock areas of foliated rock. Down at the bottom, pure foliation in these strongly deformed shear zones from Tropicana gold mine in Western Australia and the Cornishman deposit. What we're talking about here is our shear zones at different scales. And what you will learn on this course is how shear zones control the disposition of ore bodies within them. We're going to look at things like the vorticity vector of a shear zone. We're going to look at the fabrics in the shear zones, which may consist of lineations or jogs or bends, and how the ore bodies represented by these elliptical bodies may form within those shear zones. The relationship between those ore bodies and the fabrics around them is absolutely critical to exploring successfully for ore deposits which are controlled by shear zones. And I'm going to give you in the next few slides a case study to whet your appetite perhaps for the sort of thing that we can expect to get out of looking at structural controls on ore bodies in more detail. I'm going to go to the Yilgarn Craton in Western Australia. This area of very old rocks actually, which combines both granites and greenstones in pink and green colors. And I'm going to focus in on the Southern Cross province here, more or less in the center of the craton. And here is a close-up geological map of that area in which you can see the greenstones, green rocks here surrounded by the granites in white. And you can see a number of gold deposits very close to the boundary of the greenstones with the granites, just like we saw in the case in Zimbabwe. And we're going to look in more detail at one of those deposits, the Golden Pig deposit, now worked out, but having provided many thousands of ounces of gold during its production history. Here's a geological map of the Golden Pig ore bodies, and you can see that they are hosted by banded iron formations, BIF, within ultramafic and mafic igneous rocks, and that there are important shear zones which go through these banded iron formations and ultramafic rocks. And it's the coincidence really of those shear zones with those particular rocks which gives rise to the concentration of gold within this deposit, just like we've seen at a much larger scale in the case of Zimbabwe. Here is a cross-section with the ground surface up here, showing what happens below ground to a depth of several hundred meters, and a very large proportion of the ore is contained just here, where this torus shear zone intersects those banded iron formations, providing ideal conditions for precipitation of gold from hydrothermal solutions. When we go underground, we can see structures which tell us the way in which the rocks have moved, so-called shear sense indicators, very consistently indicating that the left-hand side of this picture has moved up, a reverse sense of shear. And we can put that together with our measurements from underground of the fabrics in the rock, the foliations and the lineations, to come up with a model for how the deformation has actually controlled the ore bodies at Golden Pig. And it looks like this as a block diagram, quite a complicated block diagram, but one thing to take away from this diagram is the overwhelming importance of these subhorizontal lines, such as the lineations and the vorticity vectors, which are plunging just gently towards the south and giving us a clear indication of how the ore bodies are likely to be controlled by the structures. In fact, we would predict from this work that the ore bodies must be linear bodies plunging very gently towards the south. And in fact, that's led at that mine to a very substantial improvement in the resource estimation and predictions for where additional resources may be. Before this work was done, this is a view of what the individual ore bodies might have looked like at the that view changed quite significantly after our work, and the realization of that strong control of the ore bodies by structures into this view, where the ore bodies are much more strongly aligned with that gentle southerly plunge, which we could find on the basis of measurements of the structures. So that, in a nutshell, is how structural geology can contribute to the discovery of ore bodies and their subsequent mining. Now, all of that work, a large part of that work, was done by looking at exploration drill core, which is obtained even before any mining starts. Here's, for example, collection of drill core from a prospect, a mine, in fact, in Zimbabwe, the Lulu mine. And we here see trays and trays of the exploration drill core laid out as it was drilled from underground. And when we pick up that drill core, we're able to identify structures such as veins like this. We're able to mark them on that drill core, and we're able to measure them up and use them to predict how the ore body will look underground, very much like we saw in the Golden Pig example. And here is the exploration drilling rig at the mine, which is retrieving those trays of core. Now, those ideas are absolutely fundamental to being able to predict where ore bodies may go, and also to designing, in fact, how we should drill best to find where the ore bodies are. And this is one of the slides that you would see in the exploration and structural geology or exploration and mining course, where we're showing how it makes sense to drill an ore body from the perpendicular direction rather than the along ore body direction, because simply we'll have a much greater chance of intersecting the ore body in this direction than in this direction. So we're going to learn on this course how we can design drilling programs effectively to carry out this exploration. Working with core is sometimes difficult and can involve, for example, setting the core up in a device like this and taking a compass, just like an ordinary geological compass, and measuring features within the core. There are considerable problems with doing this. It's very time consuming. And of course, it's also prone to be affected by magnetic materials. Concentrate on a different method using a device called a core protractor, like this blue example over here, to measure what are called the alpha and the beta angles. And by measuring these angles alone, irrespective of any magnetic field, we're able to measure more accurately the orientation of structures in the drill core. And this will be a large part of the end of the course, learning how to use this so-called alpha beta method. And we can combine that with what we've said previously about the structural controls in the core to think about how shear zones will look when they are intersected by core. In fact, it turns out that core is actually a great way for examining shear zones, because inherently we have the ability to look all around the shear zone in 360 degrees of view, which is not always afforded to us when we come to look at outcrops on the surface of the Earth. And from these sorts of views, we can find out directions such as the vorticity vector and lineations, which may control ore bodies. We're also going to look in the course at how folds are seen within core and learn how to measure them in terms of their fold hinges and hinge surfaces. And we're going to consider, finally, how ore bodies may be controlled by different types of geological structure. In this sort of summary table, the top row indicates ore bodies which may be controlled by planar structures, giving rise to tabular ore bodies, things like lithological contacts, as we briefly mentioned, unconformities, deformation zones, or the hinge surfaces of folds. Whereas the second set of ore bodies, which are controlled by these features, may be rather more linear in structure, like we saw at the Golden Pig example. And these may be controlled by various features of deformation zones, such as bends, stepovers, or intersections, or damage zones, or they could be controlled by boudins, between the necks of boudins, or the hinges of folds. The The course is going to make considerable use of a number of 3D models, and these are very helpful for looking at things and seeing their geometry and their relations to each other in 3 dimensions. This is a simple model, for example, for a reverse fault, which might be relevant, for example, to what we saw at the golden pig example. These 3D models will be available to you on the course, and you can have a look at them and play with them in 3 dimensions. So finally, I'll skip this video and just encourage you all to have a look at the Structural Geology for Excavation and Mining course, and leave you with these 4 images which show spectacular structures which in one way or another may control ore bodies, and throw the session open for any questions. I'd be glad to answer now.
Thank you very much for that brilliant presentation, Tom. Yeah, just if you've got any questions, please pop them in the Q&A box. While we're waiting for those to come in, Tom, perhaps you could give us a bit of an insight. I understand that the course is quite interactive. It's got quite a lot of different sort of interactivities within it. Could you perhaps tell us a little bit about that?
Yes, indeed. I think it's a very important aspect of any online course to engage people nowadays, that there is interaction. And one way that that is very much encouraged, for example, is a series of online quizzes, which occur after every significant body of learning within the course. And these are designed to test your learning and your understanding as a participant in the course. And each time you select an answer, you'll be given some feedback about whether it's the correct answer, or if it's an incorrect answer, why that should not be the case, why that answer is incorrect. And these are really have found in the number, we've now delivered this course 4 times, and we have found that the online interactive questions are some of the most effective ways really of grounding the learning that is otherwise perhaps a little bit theoretical. So those quizzes are a great thing. The other thing that we have made a lot of use of in terms of interactive facilities is the discussion board on the digital learning platform, which allows participants to ask any question, and that question is visible to all of the other participants, which is often a really good thing, because one person's question is very often the same as another person's, and the answers are posted on that discussion board at regular intervals, so that we have a record of all of those questions and their answers. So interactivity is a big thing, and we really hope that we've got a good balance between the learning materials and that sort of interactive element that will be optimal for developing people's interest, really, and maintaining their interest and deepening their learning in the course.
That's great. Thank you so much, Tom. It doesn't look as though we've had any further questions come in, so I think we'll probably wrap up there. So thank you so much for such a fantastic presentation, Tom, and thanks to everyone for attending this afternoon. We will be sending an evaluation for the Spring Online School out at the end of the 2 weeks, so we'd be really grateful if you could fill them in. Oh, I think we've had a last-minute question come in, Tom. Is that okay?
Yes, fine, please. Great.
So it's from one of our attendees. I am working full-time in WA, including stints away on site, often without Wi-Fi for adequate Wi-Fi for periods of time. How often are the questionnaires required on the course? Okay, well, this is one thing that we've been very aware of in designing the course, and it's specifically designed for people like the person posing this question, so that you don't have to do any part of the course at any particular time. You can take your time to do it within the period for which the course is available. In fact, you can do it all right at the beginning if you want, or you can spread it out, or you can do it all right at the end. So there's no limit
on when you actually need to do those quizzes, or in fact, any other part of the course. You follow the course at your own convenience. That is a very important design feature of this course. And I would want to emphasize that so that no one gets discouraged from the practicalities of their daily lives from attending this course. As long as they do have, from time to time, an internet connection, then that's going to be possible for them to complete the course at their own leisure. I would say that an internet connection is obviously essential for that, but we have broken up the course into bite-sized sessions, which take between 10 to 20 minutes to get through, specifically in order to cater for those people who can't devote long continuous periods of study to getting through this course.
That's great. Thank you, Tom. I think we had a very similar question come in on the Q&A as well about someone who's interested in taking the course but can go 7 to 10 days without internet. So you've definitely covered that off in your answer there as well. So that's great. So thank you very much, everyone, for attending. Thanks again, Professor Tom Blenkinsop. And yeah, as I say, this session is being recorded, so we'll pop it onto YouTube in case anyone wants to re-watch it at their leisure. So thank you very much, everyone.
Cheerio.
Thank you.